Hello and welcome to this CANDELA project tutorial. In this video, I would like to introduce the Docker-based system architecture and the ontological models developed for the semantic indexation aka triplification and semantic search tools. System architecture: there are two Dockers, one for semantic indexation and the other for semantic data store and semantic search. The former performs ETL process to semantically integrate raster data, such as, Open Land Cover Data, NDVI, land cover labels from DLR, change detector indicator from TALS, and geovector data, such as administrative units, cadastre parcel or forest units. This is done using ontologies describing the sources and templates defining the mappings between data sources and ontologies elements. The output of semantic indexation process is RDF graphs that are then imported to Strabon, a semantic data store on top of the PostgreSQL DBMS. It has an endpoint for SPARQL queries and data discovery interface. It is next possible to perform semantic search through a web application interface or Jupyter notebooks. Ontological models: the information contained in the semantic dataset used for semantic search is represented using the classes defined in the ontology playing the role of an integration model. We built this ontology by reusing and extending several ontologies: GeoSparkle, OwlTime, SOSA, ProO, DCat. Instead of presenting the ontology as a whole, we chose to present views on the ontology, that we call models, made of the classes and properties. Earth Observation Model: the Earth Observation Model is the part of the ontology dedicated to represents metadata of Sentinel images. It mainly describes the product an image as a result of an observation. Each observation is associated with a temporal information, its date of capture SOSA result time, and a spatial information, the area being captured, either by the geometry property of the EOM product or through the SOSA has feature of interest relation. The EO analysis model: Sentinel images are consumed by analyses defined by the project partners. For instance, they are the input data of various machine learning algorithms that identify changes between two images. The ontology provides a vocabulary, the EOAM model, to describe these data sets and to provide information about the way they were generated. The EO analysis class represents an analysis activity that takes as input one or several Sentinel images (EOM) product, and is carried out by one of the project partners was associated with an agent. The activity generates a dataset whose distribution is a raster file. The Territorial Observation Model: the model acts as the main integration model. We generalized it recently to take as input any output from EO analysis activity as long as it comes in raster files. The key role this model can be explained as follows: given a property of interest evaluated on each pixel of a raster file, the user wants to know the value of this property on each territorial unit presenting a footprint on Earth. The property could be, for instance, the land cover labels, change indicators or NDVI level. This model has evolved and the current definition is able to manage any property with its own set of indicators. The semantic indexation module is able to process any raster providing probabilistic values for each indicator on each pixel. Examples of territorial units of interest are administrative units, village, county, cadastre parcels, agricultural parcels or forest units. During the semantic indexation process, a value in percentage is assigned to each indicator of the property for each territorial unit and represented in RDF format. The property is represented using the geo-feature observation property type class. Each indicator of the property is an instance of the geo-feature observation property class. A geo-feature observation collection represents the evaluation of all the property indicators on a given territorial unit, represented with the TOM geo-feature class, whereas geo-feature observation describes the evaluation of a single indicator. The evaluation is represented using the TOM geo-feature observation class. It produces SOSA has simple result the percent value of each indicator TOM geo-feature observable property on a given territory TOM geo-feature.